All right, so you are welcome to part two of our short-term decision-making lecture. And we've done CVP analysis, if you remember. We are looking at basically four things under short-term decision-making. So we did the CVP analysis. Now we are looking at planning with limiting factor, which is not different that much from what we did under throughput. All right, so from here, we'll be looking at pricing. That will be the part 3 video. Then lastly, we'll look at relevant costing, where we'll look at make or buy, further processing, and all those things. So now we come to planning with limiting factor. All right. Just as we did in the CVP analysis, where we had the single product and the multi-product, we are going to look at a situation where you have limiting factor, that is one limiting factor, and another situation where we have two or more limiting factors, which, of course, we use the linear programming for that. Okay, so now, what is limiting factor? Limiting factor we've learned in throughput is a situation where you have scarce resources to actually meet the objective that you set for yourself. All right, so basically that is that. So let's say you have 5 laborers who helps you to produce, let's say, 10,000 units. All right, let's say a week. Then all of a sudden, what happens is that one laborer fell sick, and so you are left with 4. Now, once you are left with 4, how are you going to adjust yourself so that you can actually meet your 10,000 units, or what are you going to do entirely? So basically, that is what the entire limiting factor is what about. All right, so the constraints can be related to materials, can be related to labor, machine hours, market demand. All right, so you have to plan well. All right, so now the essence of the limiting factor is that whilst we are learning this, it will help us to optimize our resource allocation. We'll be able to prioritize. All right, so basically that is that, and it will enhance our decision making because we are prioritizing. There is one book I have here, written by Steve Covey. Yeah, so this is it. It was a very interesting book. All right, so this talks about limiting factor. It says first thing what first. All right, so that is basically the book. So if you're able to know the you within what you have in your limit, then you're able to do the first thing first. You prioritize first thing first. All right, so now when you prioritize first thing first, obviously it will help you to avoid mistakes and also get you back on your objective of producing this. So basically, that is that. Now, how do we work this thing out? Just as we did in the throughput, the same thing. Identify the scarce resource, calculate the contribution per each. We did that in throughput, right? But we did throughput limiting factor. Do you remember? So the same thing, contribution. We will calculate contribution per unit of the scarce resources. So calculate your return per scarce resources. The same thing we did in throughput. Then you rank them, all right? Then you allocate the resources, all right? That's all. You answer every question. Okay, so in your exams, it was going to be like that. So you have, they will give you a case and bring a challenge because of there is a scarce resource. And so what you have here is that, for example, consider a firm that is experiencing labor shortage in this month due to employee illness, like the one that I just described. Consequently, it's unable to produce the desired number of units. How then should production be planned to adjust, for them to adjust themselves with the constraint? All right, so let's pick our first illustration. So then we practice with the key points that we have just learned. All right, it's a very simple thing, like the way we used to do throughput. So anytime you have a limiting factor, that is the same thing you do. All right, so here we have X Limited producing 3 products A, B, and C, for which the unit cost machine hours and selling price is as follows. So these are what you have. This is the machine hours, and this is the direct material. Everything has been given. Then you have your overheads. All right. So basically that is that. All right. So you see here to be 19, and I guess you know it is 7, 9. That makes it 16. Then plus 3, then you have 19. You have your selling price, and you have already gotten your contribution. And the sales demand for the period is this. All right. The company policy is to produce a minimum of 1,000 of product A. It says that the supply. Okay. It says that the supply of material is unlimited, but the machine hours are limited, and the direct labor hours, okay, so are limited to 200,000, and the direct labor hours to 5,000. So one of them may probably be a limiting factor. So we are looking at a situation where you have these limiting factors in terms of one, and later on we will also go into when it is two. So it says that include indicate the production levels that should be adapted. All right. So remember, what did we say you do in terms of solving any question that is a limit? There is a limiting factor. Your step one that we just went through is to identify the constraints. Okay. So identify the constraints. And how many constraints do we have here? Constraints. Okay, so how many constraints do we have here? They were talking about 2, but we have to work it out to find out which one gives us those kind of constraints that we have. All right, so the scarce resources, of course, normally you always be given these situations where you are given this, but find out which one is the limiting factor. So we are told that machine hours is 1, and the direct labor hour is also 1. All right. So basically that is that. But like I said, do it to find out what you need to in terms of the machine. All right. So basically that is that. And the labor to find out your limiting factor, because we are looking at 1 in this case. So what are the products? We have products A, B, and C. All right. Then we are told that direct machine hours, then direct labor hours. All right. So these are the product. The machine hour. So this is it. Machine hour per product. These are what we have. And the next one was what? Direct what? Direct labor hours. All right. So those ones too, we have them here. Okay. So the products we have. Product A is 4,000 units, 6,000 units, and another 6,000 units. All right, so these are what you have. Then here, the hours, you need 10. So if here is 10, then basically here is what? 40,000. Because you are told, when we total, we are told that the machine hours is limited up to 200,000, right? And the direct labor hours is limited up to 5,000. So we want to see which one is the limiting factor. We want to identify that. This one is 12 machine hours. This one is 14 machine hours. So 12 by 6. That gives me 72,000. Okay, then 14 by 6. That gives me 84,000. So let me total all these things together. 84, 72 plus 40, 196. Clearly, this is not, we have excess. So So it is not a shortage. All right. We even have a space of 4,000. All right. So basically that is it for this one. Okay. And in terms of hours, this one demands 1.2 hours. So 1.2. So it will be 4,800. This multiplying this. This multiplying 0.8 hours. And this one is 0.4 hours. So 6,000 by 0.8. That is also 4,800. Then delete the 8 and put 4 there. 1.4. That is it. So in total, how many hours that will we need to produce our products? We will need 12,000 hours. That means that there is a shortage of about 7,000 hours, labor hours. So the limiting factor is equal to direct labor hours. So that is our step one. All right. So that is what we have done. Then you were asked to calculate contribution per each product. We have product A, B, and C. So what would the contribution be? I think you have it already in this question. So if you set it up, contribution is given. So product A, B, and C. Selling price was given, and so therefore contribution was given. So contribution is step 2. Step 2 and 3 are things you can do together. Contribution is 6, 5, and 4. So basically that is what you have. Then what is contribution per limiting factor? So we know that contribution is this, but contribution per limiting factor. The limiting factor is labor hours. So we are going to focus on only labor hours. So contribution per scarce resources of each product. So contribution per limiting factor. And the limiting factor, like I've said, is just the labor hour. So if the limiting factor is labor hour, then it means that the contribution that we have, we are going to therefore go through with it and now divide it by the limiting factor. All right. So what is the limiting factor for those ones? You just have to state them like the way we used to do in throughput. So this one is 1.2. We are only focusing on labor hours. 1.2, 0.8, then 0.4. Do you remember? So this one, let me push these ones down. So these are the limiting factors. So contribution per limiting factor, we change the ink. 6 divided by this is 5. 5 by 0.8, that is 6.25. 4 by 0.04, that is 10. So that is what you have done. And you can continue with the, this is the third stage. You can continue with the fourth stage. So rank. All right. So this one will be first, second, and third. Is that not it? All right. So that is that. And so therefore you can allocate to actually solve the problem that you have been given in the question. Right. So you can allocate it and solve the problem that is here. So basically that is that. So how do you go by that in terms of allocating it? It's a simple thing, and I remember I gave you a table we used to do that thing for. All right, so let's go ahead and go to do that table, because it says that the production that you are going to do for the 3 so that you can deal with the limiting factor. All right, so let's look at the units. This is just like doing throughput. There's nothing different. So we have the products. We have product A, B, and C. But in terms of doing it per your rank, I think C comes first. Then you have B. Then you have what? A. All right. So that is that. That is it. Now, we are going to, it says that indicate the production level that should be adapted for the three products to maximize. So how many are we going to produce out of C? How many are we going to produce here? How many are we going to produce here? So basically, that is the idea that you are going to do. All right. So let's look at the units. And we will look at the labor hours. Not machine hours, but the labor hours. All right. That is that. Then, I mean, we have the limiting factor in place for us to deal with it. So if you look at the products that are available, it means that we need to focus to try and produce that of. But you see, the question says that it is the policy of the company to produce a minimum of 1,000, meaning that we can produce 1,000 or more. Basically, that is that. 1,000 or more. Oh, this thing is freezing. Meaning that we can produce 1,000 or only of product A, 1,000 or more of product A to a minimum. So it means that it can be 999. If that is it, then we won't produce. So it means that the way it is going, we are stuck to produce that of A by force. Like that one must happen. The A one must happen. So you have to be very, very careful. It is the policy. You can't produce 999. You can't do this. So even though this one is the third on the rank, we must understand that as far as that is concerned, we have to produce 1,000 of that one first, even though it is the last thing. It is the policy of the company to produce that. We don't have a choice. So I think because of that, it will be prudent for us to rearrange the products again in terms of A, B, and C. Oh, I've gone too far. So in terms of A, B, and C, because policy says in terms of units of production, we have to produce 1,000 units of this. Whether we want or not, we have to produce that. You don't have a choice. You don't have a choice. So basically, that is that. We have to produce this one, the 1,000 units of this. All right. Then what else do we need to know? We know that we need to also produce that of C first. So those are the analysis you need to draw. But, you know, there is a limit, okay? We can't produce everything. Now, we know that to produce everything, how many hours will we need? To produce everything, we will need 12,000 hours with the machine, direct labor. But we have only 5,000 in terms of the hours. So we cannot do more than what we can have. All right. So basically that is that. And if we are producing 1,000 units, how many hours are we going to use? Because we are told that the standard is that for each product per hour, the price is this. But so this is it. So if you go by, if you want to know how the 9 was reached, it is 7.5 multiplied by the 1.2. That's how they got the 9. All right, this 9, which means that every hour for a product is going to be 1.2 hours. 1.2 hours. So that is that. Now, if you are producing the first 1,000, which you really don't have a choice to actually do, how many hours will you need? How many hours is that? So here, let's talk about our direct labor hour. Meaning that we will need 1,002 of product A. This is it, 1,002 hours, because that is, each hour is 1.2. So 1.2 by 1,000, that is 1,200 hours. But don't forget that our labor is limited to 5,000 hours. 5,000 hours. And product C is our major product. Is that not it? Product C is our major product. So we could have brought C here and B here, but any way you arrange it is fine. But so how many hours will product C require? Product C. So if you multiply product C, it is 0.4 hours, 0.4 hours. All right, multiply by 6,000. Can we have that? That gives me 2,400 hours. 2,400 hours. So this one is 2,400 hours. Now, how many is left? Okay, so you could also decide to arrange it like this, so that if you want, you can bring, we just brought in B. Okay, so like this. A first, because of that statement that was made. So you can arrange it like this, and you could see that you can produce all the 6,000 units. All right, so basically that is that. Now look at it. Cumulatively, this plus this is 3,600. So it means that we are left with only 1,400. 1,400. But how many would we have needed? Because this would have been 0.8 multiplied by 6,000 units. We would have needed 4,800 units to produce 4,800 hours to produce this 6,000. To produce this 6,000. Now we don't have that. So therefore, how many are we now looking at? How many are we now looking at? I can't see myself. Let me see. All right. So how many products can we now produce? Because if with the 6,000, we needed 4,800 hours. But now we can only have 1,400 hours. So how many can we produce now? How many? All right. So you can do that to know the number of units that you can produce, obviously. All right. So if every hour, all right, every 1 hour, every 0.8 hours, you can produce one, then how many can you produce out of this? We are looking at product B, because this is it. So what do we have? That means that we can produce only 1,750. Basically, that is that. That is that. Now, what is the labor cost? The wage for each hour? It should be pesos, 50 pesos. So what is the cost for us to do here? So if this is the labor hours that we are going to produce, what now is the cost for those labor hours? So you can find the cost. Then what is the money you can also generate from that? So we therefore multiply the cost and this thing, you get your contribution. So what is the contribution per unit for this? So here, product A contribution was 4. All right, contribution is 4. Product product C, what is contribution? No, product A contribution is 6. All right, product C contribution is 4, then this contribution here is 5. So basically, that is that. All right. So now once you have this, the remaining becomes a little easy for you to go in there and do, because the rest is not something that is actually a difficult thing to go by. All right. So multiply them, you get the total contribution you can get. Remember, the only reason why we had to bring the A first, this A here first, was because of a statement that was in the question. All right, why is it that I can't see myself? I see myself sometimes, I can't see myself. Okay, so there was a statement here that company policy is to produce a minimum of this. And if you don't take care and you rank B first, you realize that you can produce more of this, but you can't, you'll be having less. But it is compulsory that they must produce this. All right, so what is the profit that we are supposed to be getting? Contribution from this using these products. These are the products. All right, so contribution per unit. All right. How much is that? You can do six. The first one is 6,000, and we have 4 by 6. That is 24,000. Then we have 1750 multiplied by 5. Straight out here, this give me 8750. So the maximization plus 24,000 plus 8750, that gives me 41,000. 41,500, right? Okay, so that is that. 6,000 for 24, 8750. No, that is actually, that means I point this one twice. 38. Okay, this is 30, so it's 38.70 straight up. All right, so this is what you do, and that is it. You know how to do all these things from what do we call it? Throughput. So it shouldn't be a problem. But the problem is when you have more than one limiting factor. All right, so go through the process. All right, so we have techniques using limiting factor analysis, linear programming, shadow pricing, then marginal cost analysis. We have done all these things. So now let's look at linear programming, which is so unlikely for you to face because these things are graph. Linear program. And we use these ones when the limiting factor is more than 1. These are what we use them for. All right. Okay. So this is it. We use them, however, when there are more than 2 or more resource limiting factors, scarce resources. That is what we use. All right. So in the examination, we are going to use linear programming to actually maximize contribution or to minimize our cost, or both. All right. Okay. So these are your steps. Define your variables, define and formulate your objective, formulate your constraint. These are simultaneous equation stuff. All right. So you can go ahead and draw your graph and stuff. All right. So the best way to look at these things is always to pick up a question and do. So we are going to use these steps. All right. So step 1, we are told to define our variables. All right. Variables of constraints. Okay. So now look at the question. It says that using a step-by-step approach, what the optimum production is. I mean, you are supposed to determine what the optimum production is. All right. So let me deal with this. A video is ready. Let me deal with that and come back. All right, so let's continue. So we said that in linear programming, step 1, we need to define the variables. Define the variables. Now, what is the variable? So you can say that let X here, all right, be equal to the number of units of X to produce, or product X. And you can say let Y be the number of, because we have two products here, the number of units of Y to produce, or product Y, depending on how. So that is your first thing. That is what we have done. Then step 2, let's set up our objective. Now, don't forget, your objective is always to maximize contribution. That is what we've been doing, okay? So if you check planning with limiting factor, what we were trying to do is to see which one will best maximize contribution for us, or our profit. So you can say that to maximize profit, but here, so say, example, maximize contribution. So therefore, contribution maximization will now be equal to, now what is the contribution of X? Contribution per unit of X. So we will say 4X, because this is the number of units. All right, this is the number, plus contribution of Y, 8Y. So this is our objective. All right. Step 3, we say that in step 3 we need to formulate our constraint. These are all constraints. All right, these are constraints. So step 3, formulate your constraints. Okay, so in formulating your constraints, we have 3 departments. So here we have department A. All right, now in department A, what is our constraint? Our constraint is simple. We have department A, we have 8 and we have 10 hours here for production. So in department A, we have 8 of X as a product and 10 of Y, 10 hours of Y, which should be, we should be able to produce. So we should say that less than or equal to 11,000 hours, because we cannot exceed 11,000 hours. So that is that. That is how you formulate your constraint, because we need 8 hours. All right. So that is that. Product X hours per unit, we need 8 hours, but we are limited to only 11,000 hours. In department B, I think you can do it now. What do you need? What's your constraint? The constraint is that we have 4 of X plus 10 of Y, which we can produce more than 9 using 9,000 hours. Department C will be equal to, we have 12 of X plus 6 of Y, also 12,000 hours. So these are our constraints, all right? Then you always have to give a non-negative constraint. Non-negative constraint is also given as, so we have within 0, not greater or more than X, and what? Y. I will explain this one, this non-negativity constraint, to you very soon. All right, so that is that. What does it mean? It means that what we are producing, the production that we need to, X and Y should be greater than 0. All right, so basically that it should not go negative. All right, so basically that is that. All right, so now we have done all these ones. Normally you use a graph. All right, but I mean, here let's solve the optimal production plan in terms of you can draw your graph, but I mean, so let me try and see for you. So that will be our step 4. All right, and in step 4 we are looking at the linear programming. Okay, so this is very it's going to be very interesting. So let me do it like this. But in exam, nobody is expecting you to draw a graph. Take note of that. So on your graph, this is just a lesson. You have units. You know, we have the X and Y axis. We have units of products. So let's do something. Okay. All right, like this. So on the Y-X axis, unit of. So here was unit of product Y, 0, unit of product X. All right, so this is what we have. All right. And don't forget, we have 3 departments now. 3 departments. So we are going to draw this thing for 3 departments. But before we go in there and do, let's do some workings. Yeah. Let's do some workings. So all the constraints, all right, so we are drawing a feasible graph. I mean, we can't, what we are trying to do is to identify a feasible region, all right? So that is that. Now, so what we are going to do is that we are going to draw the constraints for all the departments. Now, if you look at department, so let me work them somewhere here. Department A, for example. What is our constraint? Our constraints were that we have, okay, so I can use it here. This is it. Okay. So to draw these constraints, we need the 2 points. So what we are going to say is that if X is equal to 0, all right, Y will be equal to 11,000. That's the meaning of this, because watch this. If you put 0 here, to be 0, here will be 0. Any number multiplied by 0 is 0. Is that not it? So it means that what we will have here, Y will be 11,000. All right. So that is the less than or equal to. So equal to 11,000. So what will happen is that, so Y equals 11,000 divided by 10. So this is what we are trying to do. So we have 8 is equal to 0 plus Y 10 of Y. Okay, so let's say, yeah, is equal to 11,000. So how are you going to do this? You are going to divide this thing by Y, by 10, sorry, so that you cancel 10, so that you'll be left with this. So this is how it will be. And by that, what will be Y giving us? So 11,000 divided by 10, that gives me 1,100. So basically that is that. Now we say if Y is equal to 0, what would then be X? So if Y is equal to 0, so let's say 8X is equal to plus 10, 0 is equal to less than or equal to. All right, so how will it be? So this one to here will go 0. So it will be X will be dividing, X will be equal to 11,000 divided by 8. So that is what it will be, 11,000 divided by 8. So that we can have the 2 places to plot our graph is 1,375. So therefore, department A, the axis to draw will be X. On the X axis, we will need 1,375. Then on the Y axis, we will need 1,100. So basically, that is how it is going to be. All right. So we will have to draw the line for such a thing. So then it means that you will have to determine a range for these kind of things, all right, so that we can fit it into. But before you can do that, do all the departments and finish so that you can have the range. And of course, if you are doing this thing, you should have a proper graph for it, a graph sheet. Okay, so similarly, if in this case in department B, if y is equal to, or if x is equal to 0, it will be 9,000 over 10. That says that y will be 900. If y is equal to 0, it will be 9,000 over 4. So on the x-axis, we have 2250. I think you now get the vibe now. Go to department C. Let me use this for department C. What would it be? If S is equal to 0, it will be 12,000 hours divided by 6. That gives you a y-axis of 2,000. Then the x-axis of to be 12,000 divided by 12 of 1,000. So basically that is that. So it means that on our s-axis, we can draw our line. The minimum x is what? What is the minimum x? The minimum x is 1,000. So we can put ranges here and say 500. Here is 0, so we can say 500, 1,000. Was there? Yeah, I think they are all like that. So 1,000. Then we have, 250 will be fine. Oh, don't you think so? So let's make this side start from 250, 500, 750, 1,000, 1,250, 1,500, 1,750, something like that. All right. Yeah, basically that is that. Because what is the maximum of x there? 1,000. Hey, yeah, then it means I need to draw a lot. I need to draw a lot. Oh, no, 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 no. Okay. So 200, 2,000, sorry, 2,250, then 2,500. I think this one is okay. Then in the same on the y-axis, I need to do a lot. Y-axis, what is the highest? I have 2,900 and 1,001. Okay, 2,900, 1,001. So let me start with, I think 500, 2,000, 1,005. Nobody has a system for this. You can do it yourself. 2,500 and so on and so forth. So like 3,000. All right. So basically that is that. So if I'm plotting, my first plot, department A, was 1,350 on x-axis and 1,100. So 1,100 will be somewhere here. So because this is 100, 200, 300, 400. So 1,100 should give me something here. Okay, so 1,100 here. And 1,100 versus what? 135, 13, what was that? 1,375. So that one will be around this range. Okay, so something around here. So I can now plot from this 1,001 to this. Like I said, in exam, nobody is going to let you do something, draw this kind of graph. My line is dancing. Good. I think this is fine. Is that not? All right. Basically, that is that. Then so this one is department A. So that is a department A. So let's name it department A. Okay, so now what is the next department? I can see C. C is even X of 1,000. This is X 1,000. Y of 2,000. So you can even draw that one. But that's it. Good. This is good. That is department C. And so when you draw this, usually add the constraint that you do, all right, the name of the line, all right, because the name of the department C, for example, is it's 12x plus 6y is equal to 12,000. Then department A was what? 8x 10y 11,000. 8 or no. So 8x plus 10y, that's 11,000 hours. Okay, then department B is 900 2250. So 2250 is here. Let me change the ink. This is 2250. And we have 900. 900 should be somewhere below this place. So it should be something like this. Okay. Department B. And the department B, it is 4x 10y 9,000. 4x 10y 9,000 hours. All right, so you've been able to draw the department for the constraints for each of the departments. All right, so now the next thing for you to do is find your contribution line. We call it the ISO contribution line. So use the same thing for your equations on the contribution. All right, you will be able to come up with that. So this is your contribution. All right, so here too, we are going to say when x is 0 and that. All right, so that is basically what we are going to do. Now, when x is 0, so the contribution, we have 4x, all right, and we have this, and we want to maximize it, all right, we want to maximize it. But the question also gave us the fixed line. Okay, so let's go back to the question. Let's go back to the question. It says that there is an unlimited demand for product X, and for product Y is limited to 600 per annum. So that is our straight line. All right. So the fixed line is 600. So we can draw that one. Where would 600 be? 600 will somewhere be somewhere like this. This graph is interesting. All right. Straight. All right. Straight to straight. Okay, so that is it. Y is equal to what? 600, right? So basically that is that. So the only thing that we are left with is our contribution line. We call it the ISO contribution line, the ISO contribution line. So now, how much do we have to, envisage our contribution to be? How much? Because the contribution here, we want to maximize this contribution. All right. So what is the contribution? Then what we do is that we will exchange the lines to find out how much we are going to get out of that. All right, so now let's look at the contribution equation. So let's assume, so this is our equation, 4x 8y. It's all based on assumption, all right? 4x plus 8y. Now, if I tell you that I'm producing the 8 of x, Then here will be like 8 units. And if I tell you that I'm producing the 4 of y, here will be like multiplied by 4 units. And you realize that this will give me a 32, and this will also give me a 32. So basically, that is that. It's just an idea of an assumption that if I'm to sell 8 units here and sell 4 units here, it gives me this. Basically, that is that. So you could clearly see the correlation that is between these kind of things. These are all assumption basis of things that you are trying to do. Now, let's say our products are in thousands. So this one will go like 8,000, and this one will go like 4,000 units. Sorry. It's a boring thing that we do. 4,000 units. All right. So that one will say that we maximize contributions of this. All right. And so you can deduce an equation from it to plot your graph. All right. So from that equation, you could say 8y 4x plus 8y gives us, let's say, 8,000. All right. And you can say where x is equal to 0, y will be equal to 1,000. And where y is equal to 0, what will it be? X is definitely going to be over 4, so that is giving you 2,000. All right, you can do same for the other 4,000 too. 4x plus 8y is equal to 4,000. So 1,000 on the y, 2,000 on the x. 1,000 on the y, 2,000 on the x. That is a far-fetched. All right, so let's do the other one and see. Okay, so let's take 4x plus 8y is equal to 4,000. When x is equal to 0, y will be what? 85. So y will be 500. When y is equal to 0, x will be, I think, 100, right? No, is it 1,000? Yeah, it will be equal to 1,000. All right, so now let's see. 1,000, y 500,000. I think it's the same thing. So you can just plot. So we are having 500 here and 1,000 here. All right, so basically that is that. Now this space, this one is our, before then we had this space before, right? We had these spaces before. And that is the free feasible area, the free area, feasible area. Let me draw that one for you. It was here, here, to this side, to this side, and to this, and to, and to this side. So we have this, 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 and this to be our feasible area. Then, because the only thing that is within this is the straight line. So we had our feasible area. That anything that goes beyond that will affect production, because if you go here, you are hitting the next line. And we have seen our ISO contribution line. All right, so that is that. But what is the meaning of all these things that we are doing? Or ISO contribution line and all these things. We need the optimal. The ISO contribution line is just telling us the combination of X and Y. All right, that will yield the same contribution. And that is why I did that side for you, that you saw 32, 32 here. It yields the same combination. All right, the same contribution. All right, so by moving the ISO contribution line as far from the origin as possible while staying within the feasible area that I have. So it means that you can only move the ISO up to only these places. That is the only place you can move the ISO. So by moving the ISO while staying within the possible range, you can find the optimum solution. All right, you can find the optimum solution. So where you have 8x, what we did. So remember, so for example, you have 8x 10y, all right. So 8x like this, 10y giving you your 11. 8x 10y giving you your 11. So 8x, for example, plus 10y is equal to 11. And you know that y was given, we were not giving, so he said that, but for the demand of product y, it is limited to 600x. So you know that your y is limited to 600. So that is the straight line that we drew. So we didn't have anything for x to draw up. All right. And that tells you that if that is the case, you have 8x plus 10, 600 here. Okay. So what is x therefore? So that is like 6,000, right? So you have 8x is equal to 6,000, 11,000 minus 6,000. That is 5,000, right? So 8x, so 5,000 by 8. So x is giving me 625. All right, so basically that is that. So meaning that my optimum production line is to produce 625 units of product X and 600 units of product Y, because that is what it is. So X will be 625 units. Y is what the demand is limited to 600. So that is what I have. Okay, so basically this is it. So my maximum contribution can now be ascertained by doing 4 of 625. And what was the other one? The contribute 8 plus 8 of 600 units. All right. So basically that is that. And what would that give me? So 625 multiplied by 4 gives me 2,500. 8 and 6 giving me 48. So 4,800. Together plus 25 gives me 7,300. All right, so that is that. So in conclusion, we are saying that the isoquant line, that is the one that is helping us to determine the optimum combination of x and y to generate fulfill our objective of meeting that contribution that we have done. All right, so you could actually do this because 600 was given. You could actually go around this without doing your graph, all right, but just because we are learning, we need to how do the graph. All right, so that is how you do your linear programming. All right, so that is that.